Most fibrous proteins like silk and the alpha keratins are almost completely insoluble in water, but the majority of cellular proteins are soluble in the cell cytoplasm. And these soluble proteins we call globular proteins. So globular proteins have a three-dimensional structure that we call tertiary structure, and that's distinct from a secondary structure. So tertiary structure refers to the three-dimensional shape of the entire peptide chain. So the alpha helices and beta pleated sheets are just part of the overall tertiary structure. Now we've seen that the forces that hold the secondary structure of a protein together are the hydrogen bonds between the amide hydrogen and the carbonyl oxygen of the peptide bond. But what are the forces that maintain the tertiary structure of a protein? So the globular tertiary structure forms spontaneously, actually, and it's maintained by interactions among the R groups, or the side chains of the amino acid. So what we're going to see is that the identity of the R groups are going to be crucial in understanding tertiary structure. And lastly, on this slide, tertiary structure defines the biological function of proteins. So it's imperative that you understand tertiary structure. Now there's four types of interactions that maintain tertiary structure. So the first one is what we called a disulfide bridge. And these occur as a result of oxidation between two cysteine residues. So here's a residue. So this is the R group from a cysteine, and it has a thiol on it. So you remember that when you have SH, we call this a thiol. And you also might remember loses electrons and becomes oxidized, or sometimes we call that oil, is an oil rig. So oil stands for oxidation is losing. So when those two cysteine residues come together, they can be oxidized to form what's called a disulfide bridge. So this is a disulfide bridge. It's got the two sulfurs in here, and that's a covalent bond, of course. And that's the only covalent bond that you'll see in tertiary structure. The next one is what we call a salt bridge, and then we're going to see this between ionic side chains. So if we have an acidic side chain that has a carboxylate and a basic side chain that has a protonated amine, what's going to happen is there's going to be an electrostatic interaction between the cation and the anion. So that's what a salt bridge is. The next one is hydrogen bonding. We've seen lots of hydrogen bonding already, but now we're going to talk about the hydrogen bonding between side chains. So if I have polar side chains, they can hydrogen bond with each other. And we'll look at some examples of that. And the last one is what we call hydrophobic interactions. This is when we have two nonpolar groups that are attracted by a mutual repulsion of water. So say, for example, I have a valine that has an isopropyl group on it, and if I have an alanine that has a methyl group on it, what's going to happen is that those two hydrophobic groups, not only will they repel water, but they're also going to have London forces, which will result in an attraction between the two hydrophobic groups. This slide covers those four interactions that are involved in tertiary structure, and you can see that our protein looks kind of interesting here. So it's got this whole piece here. So this is called a ribbon diagram, and this shows the overall shape of the protein. Now, I'm not going to trace the whole thing out here, but the reason that we do that is to show the overall shape of the protein, but we don't include all the atoms in the structure. We just use this to help guide us in understanding the actual shape or conformation of the protein. But we have highlighted some of the R groups from the amino acid residues. So I would start, here with my N-terminus, and I say I have a few amino acids, and then, oh, look here, I have a carboxyl group. And then you can see way, way further down this peptide chain, I have a basic residue. So I have the positive charge from that basic residue, and I have the negative charge from that carboxylate, and they're going to attract each other. And we call that the salt bridge. So the salt bridge is, in effect, an electrostatic interaction. Some good examples of hydrophobic interaction. So here I have the residue from a valine, and then I have the methyl group from an alanine. And not only do these hydrophobic groups repel water, but we're going to have some hydrophobic interactions based off of the London forces that they're going to feel for each other. Another example would be if I have something like phenylalanine. So I have a couple of aromatic rings over here, and of course they're both going to repel water because they're hydrophobic, and they can interact with each other. Disulfide bridges are shown down here, and of course, those are the only type of covalent bonds that are found in tertiary structure. And then the last one are hydrogen bonds, and they've just picked a couple of examples here. So here I have a carbonyl from a residue attracted to making a hydrogen bond with this hydrogen that's attached covalently to a nitrogen. Here's another one I have a hydroxyl group here, and I have a hydrogen bond between the oxygen of another hydroxyl group here. So these are just some examples of the 4 types of interactions that we see in tertiary structure. So we see salt bridges, we see hydrophobic interactions, we see disulfide bridges, and we see hydrogen bonds. And I haven't numbered these in any particular order, but I just want you to be aware that you have to know all 4 of different types of interactions that are involved in tertiary structure.